Hello, this is Professor Keene. I'm continuing my lectures on Chapter 23 of A Student's Guide, Volume 2. In this series of lectures, I've been talking about conservation of momentum. And specifically, I want to highlight in this lecture some interesting features of Newton's third law and how it's related to not only the conservation of momentum, but also some other interesting ideas. So recall that Newton's third law of motion forms the basis of the idea of conservation of momentum. Why is this? Well, it's because when any two bodies collide, they experience equal and opposite forces. So recall the idea is that Newton's third law forms the basis of the principle of conservation of momentum, right? And it's because when two bodies collide, they hit each other, the force that is exerted by body A on body B, that is force B, is exactly equal and opposite to the force that body B exerts on body A. That is Newton's third law. And so they experience equal and opposite forces. Force A equals force. All right, sorry, I had to pause. So the force acting on ball A is equal to the force acting on B. That is Newton's third law. They experience equal and opposite forces. And how does the conservation of momentum law go then? Well, because they experience equal and opposite forces, force A equals force B, and since by Newton's second law, the change in momentum of either ball is equal to, or rather proportional to, the force they experience, that means that each of these balls suffers an equal change in momentum. In other words, whatever one ball loses in momentum, the other one gains, and whatever the other one gains, the other one loses. So that is how Newton's third law forms the basis of the law of conservation of momentum. Now, I'd like to go on and talk about something else that's interesting about Newton's third law, and this is something that Newton focuses on in this Scholium that we're discussing. Remember, in his Scholia, he kind of sits back and talks about broader philosophical implications of the mathematical concepts he's developing. So what I want to highlight here is how Newton's third law helps us understand attractions. So it's also important in understanding attraction. Not just collision, but attractive forces. Okay? And he's building up to a point where he can explain his law of gravity. So imagine, so he hasn't really developed his law of gravity yet. He's just laying some groundwork. So let's suppose, for example, that you have two objects. Maybe these are magnets, for example. Object A and object B. Okay, and let's consider these to be magnets for the moment. And we already know that magnets attract each other. People had known this by this time. And so if Newton's third law is correct, then magnet B is going to pull on magnet A just as hard as magnet A pulls on magnet B. That is, force A equals force B. Okay? Now, if this was not true, if, for example, force A, let's say, was bigger than FB, we're considering a hypothetical situation. Maybe for some reason Newton's third law was violated. So this would be a violation of Newton's third law. What would that imply? What problems would arise if Newton's third law was violated? Well, this is how Newton thinks about this. He says, if, for example, object A feels a bigger force than object B, what would happen if you put another object, C, between them? Well, I'll draw some diagrams here. If this force that's acting on A is bigger than this force acting on B, then, claims Newton, what would happen? Well, object C that's in the middle would feel a bigger force pushing it to the right, we'll call this FA prime, than pushing it to the left. Again, hypothetically, if A was attracted toward B more than B is attracted toward A, then object A would be pushing on object C more than object B would be pushing on C. So then object C would feel a larger force to the right than to the left, correct? So if this is true, then this would be true. And if that object C feels a bigger force to the right than to the left, then also C would not be in equilibrium. It would not be in equilibrium. Rather, it would accelerate rightward. After all, there would be unbalanced forces acting on it. Okay, so the object C would begin accelerating to the right. So what does that tell us is that if you have this system of bodies, A and C and B, and A and B were magnets attracting each other, and C was like some other rock or something you put between them. And if A was being attracted to B more than B was being attracted to C, this whole system of bodies would then start accelerating to the right. Now, that's a problem. Why is that a problem? Because Newton's first law says that any system of bodies, any system that is not experiencing an external force should remain in whatever state it's in. So if these bodies are at rest to begin with, and if A is being attracted to B more than B is attracted to A, then it would start accelerating to the right. So this would imply in other words, a violation of Newton's first law. Newton's first law, which you'll recall, says that an object at rest tends to stay at rest, an object in motion tends to stay in motion. So a violation of Newton's third law implies a violation of Newton's first law. Okay? And insofar as we think Newton's first law is correct, the principle of inertia, we should then adhere to Newton's third law. So these two laws, what Newton's arguing here, are not completely independent. These two laws, that is Newton's third law and Newton's first law, are not independent, in the sense that a violation of Newton's third law would necessarily, at least in this case, imply a violation of his first law. Okay, now where is he going with this? Here we've been talking about magnets attracting each other, but let's think for a moment about gravitational forces. And this is, once again, Newton has not developed his law of gravity yet, but he's looking forward to developing his law of gravity. So consider gravitational attraction. And you can think about this as a hypothetical at first, right? Because he hasn't really proven that there's a gravitational attraction between the Earth and the Moon and so on yet. But so think about this as, if there was gravitation, then what would it imply? Well, he says if, for example, you take the Earth, and if these various pieces of the Earth are attracting each other, and if we were to break the Earth into three separate parts, A, B, and C, then he says, well, again, just like in this case, if object A is being attracted to B and object B is being attracted to A, these two forces should be equal to each other and in opposite directions. If they were not equal and in opposite directions, then the entire Earth would suddenly begin accelerating one way or the other, which would be a violation of Newton's first law. Okay? And now here's the interesting thing, is that you don't have to break the Earth up into equal size parts. For example, if you consider, here I considered 1/3 of the Earth here, 1/3 of the Earth here, and 1/3 of the Earth here. But let's suppose we were to consider the Earth broken up into almost 2 parts, but this one you were to break off a little part right here. So this is object A, this is object C, and this is object B. Notice again that the argument does not change. In other words, object A is getting pulled toward object B with the exact same force that object B is getting pulled toward object A. In other words, it doesn't depend on the size of the object, because if object A was not getting attracted toward object B with the exact same, that is equal and opposite forces, then there would be an unbalanced force on object C, and the whole thing would accelerate one way or the other and would once again violate Newton's first law. And so this means that if you have, for example, a small rock that's part of the Earth, or a mountain or whatever, that's being attracted toward this half of the Earth just as much as this half of the Earth is attracting that mountain. Which sounds at first a bit counterintuitive, but it follows immediately from Newton's third law. And maybe I'll give one more example that illustrates just how perhaps counterintuitive this is, but how interesting it is. Suppose we have the Earth right here, and we put a scale on the Earth, and we have U stand on the scale. U, let's take it, our object A, the scale is object C, and the Earth is object B. So when you measure your weight, what you are essentially doing is measuring the force with which the Earth is attracting you. You are measuring the force on object A, right? The scale is compressing, and it's by the compression, it's measuring the force with which object B, the Earth, is attracting object A, U. But you're also measuring the force with which you are attracting the Earth. After all, the scale is just a spring scale that's compressing because of the interaction of you and the Earth. So you could equally well say that the scale is measuring the weight of the Earth, just as easily as you could say the scale is measuring the weight of you. In other words, the Earth pulls on you with the same force as you pull on the Earth. On the Earth. That is the implication of Newton's third law. The scale measures this attractive force. It measures either of these forces. So it measures both forces. And it measures the same thing. So you could equally well say that the scale is measuring the weight of the Earth as the scale is measuring the weight of you, which is, I think, a very interesting thing. So, when you go on a date and tell your date that they weigh as much as the Earth, you are technically correct, but the date will probably not end so well.